Imagine a probe hidden inside a dark chamber. We cannot see its position, and no sensor can report left, height, or depth by itself. Instead, each sensor mixes those three hidden quantities into one reading. One reading leaves many possible positions. A second removes some possibilities. A third may isolate the probe. How can incomplete clues be rewritten until the hidden position becomes visible? Begin with a flat slice through the chamber, using horizontal x and depth z. The first calibrated reading says 2x minus c equals 2. On this slice, every position satisfying that clue forms a line. Now unfold the missing y direction. The equation contains no y, so moving parallel to y never changes the reading. The line stretches into a plane. One clue permits an entire surface of positions. Add the second reading, 6x plus 5y plus 3z equals 7. Its plane crosses the first along a line, shrinking a surface of candidates to a narrow path. Add the third, 2x minus y equals 4. Its plane cuts that path at one glowing point. The coordinates are not revealed yet. First, notice the geometry. Each equation is a constraint, and the answer must satisfy all three at once. The equations describe the picture, but repeated symbols make the bookkeeping heavy. Place the three clues in rows. Align every x term in one column, every y term in the next, and every z term in the third. Where a term is missing, write a 0, so its place remains visible. Put each sensor reading at the right. Nothing mathematical changes. We are only organizing the same information. The variable letters now become column labels, leaving a compact rectangle of numbers. Read the first row back. 2x plus 0y minus 1z gives 2. It reconstructs the original first clue exactly. The left three columns describe how the sensors combine x, y, and z. The final column stores what each sensor actually reported. The divider keeps those two roles distinct. This rectangular number layout is called a matrix. Call the three coefficient columns M. When the sensor readings are attached after the divider, call the larger layout the augmented matrix A. Augmented simply means that the answer column has been added. The names are new, but the objects are familiar. M records how each clue mixes the hidden coordinates, while A records the complete equations. The second clue contains 6x. The first contains 2x. Three copies of the first therefore contain the same 6x. Replace the second clue by the second minus 3 copies of the first. Across the row, 6 minus 6 becomes 0. 5 minus 0 stays 5. 3 minus negative 3 becomes 6. And 7 minus 6 becomes 1. The new clue is 5y plus 6z equals 1. Watch the same replacement in the chamber. The second plane pivots around its intersection line with the first plane. Every point satisfying both old clues also satisfies their difference, so that shared line stays fixed. Most importantly, the glowing common point does not move. We change the form of one clue, not the positions that satisfy the complete system. This reversible rewrite is a row operation. Use the first clue again. Now to remove x from the third. Replace row 3 by row 3 minus row 1. 2x minus 2x disappears. Negative 1y remains, while subtracting negative z creates positive z. 4 minus 2 gives 2. The third clue becomes negative y plus z equals 2. Its plane pivots around its old intersection with plane 1, and the common point remains anchored. The last two rows are easier to use in the opposite order, so exchange row 2 and row 3. Their cards trade places in the ledger. The planes themselves do not move, because no equation has changed. A row swap changes only which clue we choose to work with next. Now, remove y from the bottom row. Add 5 copies of row 2 to row 3. 5y and 5 times negative y cancel. 6z plus 5z becomes 11z. 1 plus 10 becomes 11. The entire row reduces to 11z equals 11. In space, the active plane pivots into a constant depth sheet. The other two planes meet it at the same common point. Divide every entry in that row by 11. The equation becomes z equals 1. This time, the plane does not move at all. 11z equals 11, and z equals 1 name the same geometric sheet. Scaling an entire row by a non-zero number changes its appearance in the ledger, but not its solution set. Use the new z row to clean the first clue. Add row 3 to row 1. Negative z plus positive z cancels, and 2 plus 1 becomes 3. The first row is now 2x equals 3. Its plane pivots into a vertical sheet at x equals 3 halves. We can finally read one hidden coordinate directly. Clean the second clue in the same careful way. Replace row 2 by row 2 minus row 3. Its positive z disappears, leaving negative y equals 1. The plane pivots into a sheet at y equals negative 1. Dividing the row by negative 1 writes y equals negative 1 without moving that sheet. Divide the first row by 2. The simplified system now reads x equals 3 halves, y equals negative 1, and z equals 1. 3 coordinate-aligned planes meet at the original blowing point. Check it against the untouched sensor readings. The first gives 2, the second gives 7, and the third gives 4. Every rewrite preserved the answer. The complete process is called elimination by row reduction. The method solved this chamber, but it also reveals something deeper. How many clues contributed genuinely new information? Begin with unrestricted space. One independent equation leaves a plane of possibilities. A second independent equation usually narrows that plane to a line. A third can narrow the line to a point. The number of independent constraints is called the rank. Our original coefficient matrix M has rank 3. After reduction, it contains 3 non-zero independent rows. Geometrically, 3 independent planes isolate one point. The augmented matrix A also has rank 3, so the readings are compatible with that point. Recalibrate the sensors to x plus 2y minus z equals 4, 2x minus z equals 1, and x minus 2y equals negative 3. The second complete clue equals the first plus the third. Row reduction therefore turns one row into 0 equals 0, true, but adding no restriction. Only 2 clues are independent. The 3 planes share a whole line, so both M and A have rank 2, and infinitely many positions satisfy the system. Now, let all 3 sensors report scaled copies of one clue. X plus 2y minus z equals 4. Twice that equation equals 8. And negative 3 times it equals negative 12. The numbers look different, but every surface is the same plane. Reduction leaves one non-zero row and 2 statements of 0 equals 0. M and A both have rank 1. The probe may occupy any point on that entire plane. One final calibration exposes a different failure. The clues are x minus y plus 4z equals 5, 2x minus 3y plus 8z equals 4, and x minus 2y plus 4z equals 9. On the coefficient side, row 2 equals row 1 plus row 3, but the readings disagree. 4 is not 5 plus 9. The first and third clues imply a parallel plane whose reading would be 14, while the actual second plane demands 4. There is no common intersection. Reduction ends with 0 equals 10. The coefficient matrix M has rank 2, but the augmented matrix A has rank 3. When the augmented rank exceeds the coefficient rank, the conditions are incompatible, and no solution exists. Place the 4 outcomes side by side in the same chamber. Rank 3 leaves a point. Consistent rank 2 leaves a line. Consistent rank 1 leaves a plane. A larger augmented rank leaves nothing, because the readings contradict one another. Rank is not merely a label on a matrix. It tells us how much independent information the clues contain, and how much freedom remains. This is why the lesson belongs in a path toward quantum mechanics. Physics often asks for several hidden numbers that cannot be measured or solved one at a time. Different physical conditions mix those unknowns into linked equations, just as the sensors mixed x, y, and z. A matrix preserves the relationships. Row reduction untangles them without changing their shared answers. Rank tells whether the conditions determine one result, leave freedom, or conflict. Today, 3 planes found one hidden point. Later, the same reasoning will organize much larger systems.